I'm glad to see so many people. And thanks, everyone. So my name is Chavdar Botev. I am the tech lead for the IT infrastructure team at LinkedIn, who is kind of working on Gobblin. And you already saw Vasan, who is our manager. All right, so in the first part of the talk, I'm going to talk a little bit about what our team has been working for the last 6 months or more, and I think that there are a lot of exciting and interesting new features at Gobblin that we like to share, and we'll have a presentation by Laurent, which is kind of our MVPs from the community, and he has a lot of great contributions, and he's one of the power users of Gobblin, so we certainly want to kind of see what his experience is. Of course, we also want to hear about everyone else's experience and get feedback on Gobblin and how we can make it better. So first, this is kind of what the Gobblin picture has been looking for a long time, and this is probably familiar. And Gobblin is a platform for doing scalable ingest from variety of sources or variety of protocols and mediums, and making that data available on Hadoop. And that's all great, but actually our team at LinkedIn is kind of doing more work, and it's not only ingest. And if someone was kind of listening on our support mailing list, and they'll probably see a lot of questions like that on this mailing list. When and how often is my data being made available? Can you copy this data from one Hadoop cluster to another, from one directory to another? Can you set up a retention policy for me so that we can control how much storage is being utilized? Can you optimize the data layout, the data format, so that we can run certain queries faster? Can you also guarantee the data doesn't have any duplicates, so that kind of the right metrics are being computed? And over the last couple of years, a significant kind of a number of also requests about kind of making sure that the data on our Hadoop grids are in compliance with the various data privacy legislature. So essentially, if we zoom out from the ingest picture, the picture that kind of our team has to work on every day looks a little bit more complicated. So we have the ingest on the left-hand side, but then we have multiple clusters. On each of those clusters, we actually run a number of operations and kind of doing various data processing jobs and flows around monitoring, around retention, optimization of the data layout. The data gets replicated across all these clusters. And of course, we often have to close the loop and the data going back to our side-facing clusters. So it's not only ingest. And this is kind of one of the probably the main points of kind of today's meetup is that we're moving away from just ingest and going towards what is often referred to as data lifecycle management. And this is controlling the life of data on Hadoop. So I guess this is kind of what is how data lifecycle, or sometimes information lifecycle management is defined, which is the managing of flow of systems data and metadata through the entire lifecycle, from the ingest, from the creation and the receipt of the data, through distribution across multiple systems, multiple clusters, maintenance of data, up to its deletion. And some of the kind of the key points I want to touch in my presentations about the systems that are involved in the data lifecycle management, the actual data, and the metadata. So what does the Hadoop, the data lifecycle management looks at LinkedIn? So we have to deal with a large number of data sets. Our team is managing over 10,000 data sets. And those spread across many clusters. The ownership of those data sets is spread across many teams. You often have to do processing on behalf of other teams and providing data management services. And often it's a very dynamic ecosystem, and data comes and goes, and we not always kind of are informed, or so we kind of have to be able to deal with this dynamic nature. Also, there are multiple systems involved. Most of those are loosely coupled systems working independently. Again, some of those systems are owned by our team, but of course we have to interact with upstream system where we get the data from. We have to interact with downstream system where we provide the data from. And both all the data and the systems kind of evolve independently. So it's a very dynamic, very dynamic ecosystem, which creates a lot of interesting challenges for management of data. And so one of the things we're trying is to see how we can address those challenges of just a dynamic ecosystem using Gobblin as a platform. So going from just an ingest platform to a data lifecycle platform. And we're trying to address the problem at 3 layers. Those who have already read our post, they kind of probably seen that picture. So at the bottom, this is the data set definition. I mean, this is what we process, right? So, and we have to deal with HDFS data sets, we have data sets, Oracle, MySQL, Kafka. On top, we have the operators that perform various activities related to data lifecycle management. Everyone knows about the ingest, but of course the data has to be replicated across different clusters. We have to manage the retention of the data to kind of control the storage, to control the lifespan of data, so that we're always in legal compliance. And the top layer is kind of trying to fit everything together. And I'm going to try to address each of those layers. So first, the data sets. And the most important parts about the data sets is that they're ubiquitous, right? So we mentioned that data sets who live on HDFS, lives in Hive, data sets who live in Kafka. They're heterogeneous, so it means that data layout, the data format of the data is different. So often it's it's hard to find the common part, and kind of what we have identified, that at least what most important part for data sets, we have to be able to identify data set. And those of you who can kind of following our commits, they see that we are more and more talking about data sets URIs and data set URIs, giving each data set a name and being able to reason about this data set by its name, and trying to standardize on name nomenclature so that the different system kind of make sure that they're talking about the same thing. The other thing that is important about the data sets is that there's some additional metadata that's associated with the data set. And I'm going to talk a little bit more about metadata later. So the operators, I already mentioned, there are lots of operators: ingest, replication, retention management, data deduping, etc., etc. And often for there may be multiple implementations for the same operator. Sometimes because a system kind of gradually evolve over time, all the systems are replaced by newer system. Sometimes you have different implementations which address some very specific use cases. And finally, the metadata. Like data, it's ubiquitous and heterogeneous. It lives everywhere. Metadata may be the file, the name of the directory where the data set is located. Maybe part of the name if it has, for example, the record count in a specific data set. Or it may live in Zookeeper. It may live as a attributes in Hive. It may live as nodes in Zookeeper. Again, what's the common about the metadata? It's always associated with the data set. And this happens to the data set URI. And it can be represented as a collection of key value pairs. And in Gobblin, kind of the two main points where Gobblin interacts with the metadata. One is the dataset configuration, and this is some new feature that we've added to Gobblin, and we have a presentation later today about how we manage the inputs that controls the Gobblin processing. And also the metadata lives in the output that we produce. And the primary mediums that Gobblin kind of emits that metadata, these are already the Gobblin metrics and Gobblin tracking events, which have been there for maybe over a year. So I hope some of you are already familiar with them. Okay, so we have the data set, we have the operators, and we have the metadata. So how do we make it fit together? So this is the orchestration, the top layer of the original picture. So the most important part is that we look at the dataset operators as independent actors. So each of those are independent systems which know how to do one specific task, whether it's the ingest or the retention, the replication, but generally they're not aware of the rest of the system, which kind of allows to have very flexible data processing flows. Generally, the interaction between the different operators doesn't happen through fixed flows, but happens through a shared state. For example, typically we have to ingest the data and we have to replicate the data across the different clusters, but this is not encoded as a flow. We don't have a flow which says, oh, first read this specific table and then copy it to clusters A, B, and C, because this approach scales if you have to do that for a couple of tables, but once you have to do this for a couple of thousand of tables, then this approach doesn't scale. What we do is the ingest, the interaction between the ingest and replication happens through a shared data directory. So ingest reads the data, writes it to a data directory. The replication continuously monitors, oh, is there anything new in the directory? And it will replicate to the other clusters. The same thing is with the retention. We always have to run retention on the data, and there's no the share set again is the data directory. And then other ways to share the directory, share that state. It may be through the configuration where it says, oh, the ingest is going to produce data sets which have a specific tag, a specific metadata attribute. And then the replication knows that, oh, I'm responsible for replicating data with this specific tag. So this is the shared state. And essentially the data sets and the metadata are the common language for which the different operators talk among each other. There's also a shift towards continuous execution. Again, once we have to start operating at the level of hundreds and thousands of data sets, the typical batch model in Hadoop starts to kind of not scale very well, especially if you care about the data availability, care about predictability. And this is where we think that the execution model comes. So originally, we have originally started with the single node Gobblin execution model, then kind of trying to scale out the execution model with MapReduce, and now we are actually going even beyond MapReduce and going beyond the batch-oriented processing and trying to run continuous data lifecycle management. We kind of we started last year this work on integration of Gobblin and be able to run directly on Yarn. We have some interesting new features, and we have a demo around Gobblin integration with, for example, AWS, and being able to run Gobblin on AWS, and ultimately being able to integrate to the data resource management frameworks too. So this is so nice and great, and so maybe some people who are familiar with other systems like Falcon, which kind of do similar tasks, would say, so okay, so why do you have to do all of that? So why don't you just use Falcon? And I think that Falcon is kind of has its specific target audience, but at least for our purposes, we found that Falcon has a number of limitations. And at least from my point of view, Falcon has a top-down approach. It's trying to define everything, the whole ecosystem, all the data feeds, all the processes, and try to centralize that description in a single location. This creates a very tight coupling between all the different actors in the data lifecycle management, which limits the flexibility of what we can do. Falcon, it's not easy to do multi-tenancy. It's hard to say this specific process can process just should be able to process just 5 data sets independently. There's also the lack of data set auto-discovery. If a new tracking topic shows up, we can't just ingest it automatically and kind of replicate it automatically to all the clusters. You have to define a specific feed. You have to modify the different processes to be aware of the new feed. So it's a lot of manual work. Lack of policies. Once you start going to tens or hundreds of thousands of data sets, you have to be able to group the processing of similar data sets together, so they kind of manage them as a single unit rather than individual data sets. This happens through policies, and we have some discussion on policies in our Gobblin configuration presentation. Also, the flows in Falcon tend to be less flexible. To kind of give you an example, let's say that we have an ingest of data from OLTP, and we have both the snapshots and append data being ingested. And let's say that there's an issue with the append data ingest. So typically what we have to do at this point is not to be able to affect the downstream consumers and not to affect the data availability. We want to turn off the append ingest, but make the snapshots ingest more frequent so that the data is still available on Hadoop. And doing this kind of flexible switching of all append data sets to a snapshot mode is not easy through kind of the static configuration that Falcon provides. And ultimately, Falcon is primarily batch-oriented, so it's not very fit for continuous execution. So to try to wrap my presentation, I went for 5 minutes overtime. It's more than just ingest. It's data lifecycle management, and we're trying to address multiple aspects of the data lifecycle management. We think that the best approach that can allow growth, and both in terms of processing lots of data, addressing different data, different use cases is through loosely coupled systems, so that you can evolve your architecture over time without having to rework everything. And again, it's a data-centric processing. Jobs don't give you enough flexibility to be able to customize your processing when you have to deal with thousands of data sets. You have to think about data set and specify, oh, this is what I want for this